So some of the characteristics at temperature and room temperature, so the temperature is either room temperature 140C, the IV curves, the quasi-static, the pink trace here for tungsten is the erase of the 140C, looks significantly different than it does at room temperature, but you're still getting switching. And the chromium, it looks very neat, and it was a really stable device when you add the chromium to it. The tin, this one with the Co-Sputtered tin, looks a little bit rough, but it worked as expected. And we did a simple tungsten single point 33 millisecond DC type application of potential and traced out an IV curve for that. We're going to focus on the tungsten device, and that's the one we're going to do the demo on today. We probably would have done the tin or chromium, but we couldn't get them outside of the US at the moment. So the room temperature versus 140C, sinusoidal response, going from 0.1 hertz, where you've got really nice, in this black trace, nice wide lobes, up to 100 kilohertz, where it's a flat line, shows the generic Memristor response. It does also at 140C. You can't see this one very well, but at about 10 kilohertz, it's this nice light pink line. So it definitely still responds as expected. And I did want to point out that the tungsten devices tend to get a smaller negative lobe than positive lobe. So it gets to be a little uneven as you operate these, and we're still trying to understand what's going on with that. And you've seen this one earlier. This is from that device, the tungsten device, trying to walk up the conductance, essentially change the resistance as we apply consecutive right pulses, and it does. And it actually does this better than the tin system. That's why we chose this one. The tin system, it's difficult not to jump too far, but this one tends to like to go to the intermediate states better. Same with the erase. I did want to mention also that if you apply a DC potential for a long enough period of time with this, even if it's subthreshold from the normal DC quasi-static sweep, you can hit the device to write. So in this particular example, the device was writing with 0.13 volts, even though that's below the threshold value, which is at about 0.2 with the short integration time DC sweep. It does write, and as you increase that potential and apply DC, it writes at a lower and lower switching time with something like this. I tried to use a 0.12 and even lower potentials, and I couldn't wait long enough for the devices to ever switch. It just didn't respond. We sat there for 1,200 seconds and longer, and they wouldn't do it. That doesn't mean they won't. And then just a quick discussion. We started to look at the sweep rate and switching time effects on switching voltage. And we looked at temperature, so 2350, 100, and 140 at 4 different device sizes. These are all really large devices, but we still should see some effects. And we didn't see any effects due to device size, but we did see some small thermal effects. As you'd expect, the threshold voltage decreases. You can see that better here. Switching voltage as a function of the sweep rate for each particular case. It's a bit noisy, but and switching voltage is a function of the switching time for that. And we're still kind of working this out. This is new. So I know that we've got some things to say, but we're not there yet.